Now we can go on to our next presenter, Jennifer Morris from Massachusetts Institute of Technology.
All right, so hi, my name is Jennifer Morris. I'm a research scientist at the MIT Joint Program on the Science and Policy of Global Change. And the work I'm presenting today is on water-related threats to Indonesia's economy. And it's work that I conducted along with Sergei Paltsev, Brent Bollert, and Ken Strezpek. So the motivation for this work is that climate change will impact both water quantity and quality. And while much work has assessed physical impacts, economic assessment of water-related threats has proved quite challenging. And so the goal of this work was to try to incorporate some of these water-related threats into economy-wide modeling to assess macroeconomic and sectoral impacts, as well as impacts of some actions to mitigate threats. So we use Indonesia as an example to illustrate our approach, which can be applied to other regions and settings. And so Indonesia faces a number of water-related threats that are expected to have potentially severe macroeconomic consequences if not addressed. These include inadequate water supply and sanitation coverage, or we refer here as WASH coverage, sea level rise and subsidence, flooding risk, insufficient water storage, peatland and lowland degradation, and water over extraction. And development and climate change will exacerbate these challenges through growing populations and demands for water, as well as more severe droughts and floods, for example. There are also a number of potential responses to these threats. And we captured a subset of these responses in our modeling as well, those in red, things like improving access to water supply and sanitation, improved land use, building water supply reservoirs, and others. So to incorporate these threats into an economy-wide model, we employed a biophysical economic modeling framework as depicted here. And so we used various sets of data and assumptions, for example, historical data, future climate projections, for example, from the CMIP exercises, development projections, along with different scenarios that we explored depending on the threat or the response being examined. We also employed a series of biophysical models to provide input for the economic model for each of the threats. These include models for rainfall and runoff, for flood peak, and for reservoir water balance, which also captures supply. And then we spent a lot of time carefully considering impact channels or pathways by which water-related threats or responses can affect the economy. And the magnitudes of the shocks that we implement in the economic model for each of these pathways are based on the biophysical modeling, as well as estimates and assumptions pulled from the literature. And finally, the final piece is a country-level, economy-wide, computable general equilibrium model for Indonesia. This model includes 26 sectors, 4 factors of production: capital, labor, land, and natural resources. And it has a forward calibration procedure to project GDP, emissions, and other outputs for 2030 and 2045, allowing us to estimate the sectoral and macroeconomic impacts of these water-related threats, or in other words, the cost of inaction, as well as a subset of responses or the benefits of action. So each threat that we considered has multiple impact channels, and the table on the right lists the full number of channels. However, the main channels of impacts are related to population and labor force, specifically labor productivity, capital, both sector-specific capital as well as a mobile aggregate capital, health-related costs, energy costs, water supply cost, or the capital spending by government and industry, as well as agriculture in terms of land availability and productivity. And so a full description of each of these channels and their magnitudes are described in a World Bank study from 2020. And each of these set of scenario-specific results are compared to a base case for 2015 to 2045. So as many will recognize, an approach like this, kind of in general, the steps for this channel approach is to first specify the scenarios, second specify the impact channels and the specific hooks to the CGE model for the impacts as well as the investment responses, then to estimate the magnitudes of the shocks for each of the hooks, and then to implement the shocks in the CGE model. So as an example to walk through this, this was the process for the WASH channel for improving water supply and sanitation. So we first decided on the scenarios for this channel. We went with business as usual with constant WASH coverage remaining at the 2015 shares throughout the time horizon, and a full WASH coverage scenario that achieved 100% coverage by 2045. We then specified the channels and hooks into the CGE model, which include labor. We're capturing an increase in future productive labor hours due to reductions in sickness, childhood stunting, and childhood mortality, which enters the model in terms of increased labor productivity. We're capturing direct savings in healthcare costs by lowering the cost of the human health sector in the model. We're capturing reduced fuel expenditures for boiling water, which actually was a significant energy expenditure in Indonesia to get clean water by boiling it. And we implement this in the model by lowering the cost of the non-transportation energy consumed at the household level in the model. And then we're capturing also fishing, improved fishing yields due to the investments in sanitation. The cleaner water results in better fishing yields. And so we implement this in the model through increasing the endowment for the fresh aquaculture portion of the non-land agriculture resource endowment in the model. So those are the channels, and then to estimate the magnitudes of the shocks of each of these things due to the WASH investment, we rely on population projections and development goal trajectories to estimate the number of individuals who would have improved access to WASH. And then we did a vast review of the literature to pull out relationships from the literature on drivers to health outcomes and additional sources from the literature to allow for translation to labor productivity, and then estimated the changes in labor productivity relative to the base case. And we took additional estimates of the what it would cost to implement these WASH improvements and implemented those costs in the model as reduced government capital. So the government is spending on these investments in improving sanitation. So we put those in the CGE model, and then the table on the left shows the shocks that we implemented in the model for labor productivity and the health and energy costs. And the table on the right shows the GDP impacts of the improved WASH coverage. So this provides, I'm not going to go through all the numbers, but just to give an overview of the type of process we went through in this study. And we can see that for the improved water availability and sanitation, there's overall net benefits of these investments, even after accounting for the cost of the investments. Quickly, another example is to walk through is flooding, where we explored scenarios related to different land use or land degradation, climate change, and flood levels. We also specified channels related to capital. So the disruption in capital due to flooding was implemented as decreases in both sector-specific and aggregate capital. And also we captured the indirect effects of labor productivity from displacement as decreased labor productivity. And then we employed flood runoff models for each of the 752 drainage basins in Indonesia. to estimate peak flood magnitudes. And then we combine this with estimates of in the literature for damages for different types of infrastructure and labor productivity, and aggregated those to ultimately get to the national level. So again, not to get into these numbers, but just to provide a sense of what went into this work. Sure. The table on the left provides an example of the types of capital shocks we input into the model, and they're by sector and for the different scenarios, and also the labor productivity shocks we put into the model, and then finally the GDP impacts of those shocks. And we can see here that labor productivity impacts are very important and have large negative impacts, and the combined labor and capital impacts are more than additive, as there are some interaction effects, which we can also capture in the model. This table provides a high-level overview of the different impacts, and we can see that some of the top threats considered here are for insufficient water storage, for flooding risk, for sea level rise, and groundwater over extraction. And we can also see that the responses considered can have significant benefits of those actions. So I know this is kind of a whirlwind, but just giving an overview of the type of results that we find with this approach. We also combined the various impacts through exploring 2 combined scenarios of future climate impacts, a low impact and a high impact, and 3 different levels of action: limited, moderate, and aggressive action. And the overall GDP impacts in 2045 with limited action range from about over 3.5% to over 7%. However, pursuing moderate action to the various water threats reduces impacts by about 1 percentage points, and aggressive action can curtail those threats and cut GDP impacts nearly in half. So there are some policy relevant findings from this work. I won't go through them all now, but clearly climate change poses a significant risk to growth. We saw this in the sea level rise, the flooding, and potential water shortages due to drought. So it's important to build resilience to those risks. Investing in water supply and sanitation is a clear winner in this work. Also, additional reservoir storage stood out as an action that posed multiple benefits, those related to food security, making water available for irrigation, as well as water security, and the ability to reduce groundwater pumping and its impact on subsidence. And we also found some interesting results related to peatland and lowland development for agriculture, whereas there's near-term economic benefits of that development, but by 2045, those gains are already turned into a GDP loss due to subsidence, induced flooding, degraded productivity, and additional emissions, which bring greater costs for meeting NDCs. So as a summary, this channel-based impacts approach can be used to connect biophysical and economic models, specifying the pathways and magnitudes of shocks of water-related stresses, as well as responses in an economic model. And we used Indonesia as an example to do so. For Indonesia, we found these threats to have significant negative impacts on GDP, up to over 7%, but aggressive action could curtail those threats, cutting them almost in half. This approach can be applied to other regions and settings, other types of threats and risks. And one thing that stood out in this exercise was the value of quality data and sectoral analyses that were critical for our economy-wide analysis, as we found tremendous value in pulling from existing studies and data sets in the literature. So with that, I thank you for your attention and look forward to the rest of the session. Thanks.
So our next presenter is Yasmin ROMITTI from Boston University.
Hello to everyone. My name is Yasmin ROMITTI, and I'm a PhD candidate in the Earth and Environment Department at Boston University. I'm going to apologize in advance because I'm just getting over my first cold in 2 years. So my voice is still not 100%, as you can hear, but I'm going to do my best. Thanks for logging on. I'm going to give an overview of a project that my mentor and co-author Ying and I worked on, characterizing urban energy demand across a set of global cities, and how that demand is projected to change under mid-century warming. So this work is really motivated by the need to understand what effective climate adaptation means for cities and urban populations across the world. So we know climate change is projected to increase ambient temperatures and urban populations' exposure to high and extreme heat. This has important implications for population health and energy demand. High heat has a variety of heat-related health consequences. And if we plot temperature against energy consumption, so here electricity, we see that above and below some set point temperature, depending on where you are in the world, the energy demand increases both for heating and for cooling. And we're specifically interested in cooling demand. Why cooling demand? Because a key mechanism of heat adaptation is the use of air conditioning, and future projections of energy demand expect that under mid-century warming, we're going to see reductions in the demand for various fuels for heating in the winter, accompanied by increases in the demand for electricity for summer cooling. But the extent to which these two phenomena will offset each other is going to vary across different geographies, different timeframes, and under different degrees of warming. So that really highlights our need to basically assess how urban residents' attempts to cope with this higher and more intense heat is going to manifest in terms of energy demand consequences. So prior work in the empirical climate impacts literature has produced estimates of future mid-century electricity demand, but a couple things, these estimates have relied on country scale measures of electricity consumption, which will mask local heterogeneity in the response. They've also relied on daily series of future temperature from global climate models when we know that exposure occurs over much finer timescales. And also energy demand depends on the unique characteristics of the built environment. So that raises this question of the importance of using a lag structure to model the association between temperature and electricity, which is what is commonly done in the epidemiological literature when they model the association between temperature and morbidity and mortality. So what we do, What we do is take advantage of an existing data set of hourly electric load, and we use that to quantify the electricity demand consequences of adaptation to temperature change under two RCPs, 4.5 and 8.5, across 36 world cities, some pictures of which I've included here on the right. And we do so by drawing on the breadth of empirical literature that describes temperature's effect on the demand for energy in general and electricity specifically. So in particular, we draw from the analyses from Maximilian Afhammer and Leonie Wentz in order to estimate reduced form statistical models of hourly electric load to hourly and lag temperature. And then the next thing we do is we temporally downscale projected mid-century temperatures from 21 global climate models to an hourly time step, which allows us to then couple our temperature demand response surfaces with these projections in order to come up with projected hourly impacts to urban electricity demand. And the cities we analyzed, as you can see, they're depicted here on the right. Our sample primarily spans North America, Africa, and South Asia. So we divided our empirical approach into three main parts. We first estimated the nonlinear response of cities' hourly electric load to lagged hourly temperature using a general additive model. And we used an existing data set, as I said, on hourly electricity consumption. And this was collected by the Sustainable Engineering Lab at Columbia University. And we used that in conjunction with meteorological data from ERA5. And what's important to note is here, psi is a tensor product, and that is what allows us to implement a lag structure to account for the interaction between hourly and lag temperature effects. So this allows us to include the effects of unobserved thermal inertia of the urban built environment, as heat can be cumulatively stored in buildings throughout the day. And we chose a 6-hour lag. Our fitted response has its lowest point at what we call T star. And this is where weather sensitive electricity load is minimized, and minimum load is denoted as L star. And we can interpret this as the fractional increase in electricity above L star per degree Celsius above or below T star. And the next thing we did was to temporally downscale, as I said, the daily maximum and minimum temperatures from 21 global climate models in the NASA Earth Exchange Global Daily Downscaled Projections product for RCPs 4.5 and 8.5, although I'm only going to show results from 8.5 today. And also, just so you know, this was CMIP 5, not CMIP 6. And so what we did is we said, okay, hourly temperatures, we assume a stable relationship between, you know, the daily extrema for the day, between the max and min temperatures, so that you can model the hourly temperature as a convex combination of daily maximum and minimum temperatures. And that allows us to construct a synthetic hourly temperature series, which includes an index of current and future periods. And then with that, we are able to estimate hourly electricity demand impacts by evaluating our fitted response surface at current and future hourly temperatures, with the assumption and the caveat here being that this demand response function and therefore the structure of electricity demand remains constant in the future. So in the interest of time, I'm only going to cover a quick subset of our results. So essentially, I'm going to talk about 3 things. How does demand respond to temperature across our different cities? How are hourly temperatures going to shift in the future? And then the relative impacts across the cities that we looked at. So here I show the demand response functions from our initial model estimation. And I just chose 4 cities to show you. We observed 3 main categories of response type across different cities in our data set. So we have these V-shaped splines, which you see here in Chandigarh and Boston. And this is the response type that you typically find all across the literature in this field. We also saw an increasing response type, primarily in tropical cities. So as in Manila here, as well as a couple cities that exhibited an unresponsive response type, which is what you see in Nairobi. So if I now bring up a map again of the world cities, and this time focusing on the color coding, which basically corresponds to the spline classification, the broad pattern that you see is that mid-latitude temperate cities exhibit the classical V-shaped response, and tropical cities largely show either the increasing response or are unresponsive. So it's evident that the splines embody the local structures of electricity demand, different latitudes, macroclimates, local urban climates, as well as different levels of development. And the last thing that I'm going to show you pertaining to the demand response function is this is a 3D surface of the partial predictions of demand to temperatures at each individual hourly lag, which is what's on this like y-axis here. And so you'll notice that if you broadly look across the surface, you'll see the general shape of the spline for each city. So essentially the plots here on top is they represent the cumulative response to temperature integrated across all lags. Whereas when you look at the surface, you can see it, what's going on in individual hours. And then just very quickly, looking at the projected shifts in seasonal temperature distributions for each city under RCP 8.5. I'm just showing summer and winter here. But what is important to note is that by using this hourly temperature series, we actually see that the temperature distribution shift is slightly larger in temperate cities over tropical cities by about 1 degree in the summer and ½ a degree in the winter, which represents a shift in some previous work, which largely looks at how these distributions have shifted. They do so using larger temporal scales. And then this is sort of like our big picture result is sort of the percentage change in demand impacts. So on the left, I have annual per capita demand, and on the right, I have peak demand. So what happens at the 95th percentile of demand? We've color coded the cities according to their spline classification again, so you can kind of see how they rank. And if we just focus on the left here for a second, you see that, okay, overall over the year, percentage impacts are modest. At the multi-model median, impacts range from a decrease of -2.5% all the way to an increase of 6%. But for the majority of cities, they're in this sort of 0 to 5% range. And in addition to there being variation among different cities across the world, there's also variation across global climate models. However, if we only focus on the net annual impacts, this really obscures the effect of what's happening at peak demand, which is what you see here on the right. For some, to a 10% increase in per capita demand at the multi-model median. And moreover, if you look at how the cities rank, you'll see that the largest impacts are concentrated in mid-latitude temperate cities. Okay, so this is just a snippet, but basically taken as our whole, our results demonstrate that the electricity demand consequences of climate adaptation really vary with their latitude, the structure of electricity demand, and the thermal inertia of the built environment. So just to quickly reiterate, we saw 3 categories of demand response to temperature: V-shaped, increasing, and unresponsive. We see slightly larger shifts in projected temperature distributions over the year in temperate cities relative to the tropics. We see the greatest impacts for peak demand in the mid-latitudes. However, and if we look at net annual demand, the impacts are more modest, but this obscures, the redistribution of cool season reductions and warm season increases, which is what you really see at the peak. And then, so overall, our results really imply that the structure of electricity demand and the thermal inertia of the built environment is much less responsive to temperature in the tropics, so their responses are much more inelastic. One of the big takeaway messages we had here is that the prior demand responses that have been estimated for these developed temperate regions are really not likely to reflect the temperature dependence relationship for electricity consumption that is in the tropics. And more importantly, it really highlights the need for more studies of this type across different areas of the world, especially in the tropics, and especially at this fine spatial and temporal resolution. So I have a couple references for you, and that's all I have. I have some acknowledgements. Thank you all for listening, and look forward to the rest of the session and any quick questions.
Thanks, Yasmin. We have one question in the chat, which is, what does a city's electricity load mean here, and how can these data be collected by point globally?
By point globally. So this is hourly load collected from either the utilities or the load operators in an area. Because we didn't collect it ourselves, I can't speak more sophisticated, any more sophisticatedly as to who they contact in each city for these data. And essentially, if we wanted to get observations for cities around the globe, the issue here is that we really only have large amounts of data for basically a lot of developed countries, and we have less data for the sort of developing tropical areas. And it has to do with just who is in charge of these data. Who do you go to the utility? Do you go to the relevant government entity? So I think if you wanted a consistent data set for the world, you'd really have to start some sort of consortium to store all the data and to contact people.
Thanks, Yasmin. I have a question as well. So the tropics are showing up as a different response, which you noted. Can you explain what's driving this? I didn't catch that.
Yeah. So the V-shaped response that we see, it's because, typically in a normal temperate region, you have a demand for heating and for cooling, and you have a very large temperature distribution that is experienced throughout the year. In the tropical cities, you have a much smaller temperature distribution. So maybe it only ranges from 25 to 35 degrees throughout the year. So they really have no heating signal. So that's why you see a lot of just that increase, sort of monotonically increasing response, because you only have a cooling signal. And so where load is minimized is sort of like the bottom of the temperature distribution. And for the unresponsive cities, we're a little bit not sure. It's either, the data that we have that some feature or some idiosyncratic, due to the geography of the specific cities, but we couldn't parse that.
So is the response itself actually different, or is it just that the range of the data are different? So you're only capturing the increasing part in the
It is
tropics?
also different because if you look at the slopes of, we basically took the slopes on either side of the weather, like the minimized temperature to kind of indicate how elastic or inelastic your response is. And in general, the tropical cities that we had a much more inelastic response, even for that cooling signal. And so it wasn't that steep, with the exception being like Manila.
Okay, thanks. And our last presenter is Ying ZHANG from PNNL's Joint Global Change Research Institute.
Hi, everyone. I'm Ying ZHANG. I'm a research associate at the Joint Global Change Research Institute. It's located at College Park in Maryland, USA. Today, I will present modeling Arctic offshore oil in a changing climate. This is a joint work with my colleagues, Siwa Masangi, Stephanie WALDHOFF, and JiaBin. And the work is funded as a part of the Interface project. So you can see the big logo here, where the Interface stands for Interdisciplinary Research for Arctic Coastal Environments. So the project covers a wide range of research tasks, from local studies to Earth system modeling that centered on the potential changes across the Arctic coastal regions. In this study, we're looking at how the melting sea ice under climate change and other global social economic drivers could affect the extraction activities of Arctic offshore oil and gas. But for this presentation, we will only focus on the Arctic offshore oil part for simplicity and for explanation of our overall methodology and some of the preliminary results. So as you know, climate change has led to sea ice loss, which will continue to open up new regions in the Arctic for human activities, such as the offshore oil extraction and shipping. In other words, some Arctic oceans, which were originally covered by very thick sea ice, may no longer be difficult to access due to the sea ice loss under climate change. So resources, including the oil resources under the ocean, could be accessed more easily than before. The top photo from NOAA shows several scientists in the Arctic, where in the Arctic, the new research predicts ice could disappear in the summers within the next 30 years. The USGS, the United States Geological Survey, has assessed the undiscovered oil in the Arctic to be 90 billion barrels, which are approximately 13% of the world's undiscovered oil. And it's also 3 times the global total crude oil production in 2015. A majority of this undiscovered oil in the Arctic, north of the Arctic Circle, are also offshore. Here shows another picture of the Arctic, where an offshore platform for oil production in the Petroral Sea in Russia is sitting on the thin ice. The field's offshore oil production started in 2013 and has continued since then. It's reported the field can produce 0.2 exajoules per year, or that's about 100,000 barrels per day at peak. In 2020, the annual production is around 70%, so 70% of its peak production level. While there's likely to be oil resources in the Arctic and there's already extraction activities of Arctic offshore oil, the future of Arctic offshore oil extraction is, however, unclear given uncertainties in sea ice conditions, among other factors. The extraction of Arctic offshore oil can have potential implications for not only fossil fuel markets, but also for Arctic shipping and the associated carbon emissions. So in this study, we applied GChem with a newly developed representation of Arctic offshore oil to explore potential Arctic oil production under sea ice losses. As most of you probably know, GChem stands for Global Change Analysis Model. It's an integrated assessment model which operates across multiple systems and scales, such as energy, land, water, and economic system. On the right, There's a flow chart for the energy system in GChem, going from the resource production, energy transformation, and then to the end use sector. The representation of Arctic offshore oil resides as a sub-resource under the crude oil, where the total crude oil production would go to the crude oil international trade market, or it continues to the liquids refining as in the energy transformation, and eventually to the end use sectors in regionally differentiated market in GChem. On the left, there's a map showing the mean estimated undiscovered oil by assessment units, or AUs, initially in an USGS published report and later published in a science paper by Gautier and its co-authors. We implement this undiscovered oil potential at the AU level to GChem with AU-specific Arctic offshore oil resource reserve technologies. By doing that, we are able to model the potential production in each of the AUs. So to incorporate the climate change impacts on sea ice laws, we obtained the sea ice thickness projections from CMIP6 model ensembles under 3 SSPs. As an example, I plotted the annual average sea ice thickness in the 6 AUs in USA as shown right here. So each color band includes multiple model ensembles under a SSP. The red band is for SSP 585, where the sea ice thickness is the lowest in general, and in particular at the end of the century. There's also AU by AU differences. For example, the Hope Basin and the Alaskan platform right here have generally lower sea ice thickness than other AUs. The temporal window or the seasonality of sea ice thickness is critical for offshore oil extraction technology implementation. On the right, there is the monthly sea ice thickness across the same 6 AUs. X-axis is the month and Y-axis is the year. So the yellow color means 0 sea ice thickness, and the deep blue means thickness at or above 1.5 meters. The viable offshore oil and gas extraction technology can be defined based on this window. For example, the subsea tech can be implemented in 2015 at the Alaskan platform, while a cheaper tech, floating, can be implemented only around 2070, as it requires all year round sea ice thickness below 1.5 meters and no longer greater than 1.5 meters in the future. As a result, based on the sea ice thickness projections, we can divide the assessment units into 3 categories: untapped, only tappable by subsea, and tappable by floating. And this can vary over time. The cost functions we developed depend on the sea ice thickness and also the viable offshore oil extraction technology, given that temporal window. As an example, on the right, I have the estimated annual extraction costs given sea ice projections in one climate model ensemble under 3 SSPs, or purposely I call it RCP here to differentiate with the GChem SSPs. So in general, RCP 8.5 leads to lower extraction costs, which is indicated in the orange line here. So driven by the economics and dynamics in GChem, including the energy demand and then the competition with other resources in the model, we show that Russia would start to tap the Arctic offshore oil in the beginning of the modeling periods for all climate scenarios. For this model ensemble I'm showing here, USA and Canada and Greenland will not likely to tap the oil before 2100 under the reference with no sea ice change in the future periods, and the reference with the sea ice projection under RCP 2.6. While under the RCP 8.5, USA and Canada will not tap the oil until 2070 or later. So in general, we can see that RCP 8.5, that's again, the orange line here leads to earlier and higher Arctic offshore oil production. However, in Norway, only slight differences are shown across different RCP scenarios, the climate warming scenarios, mostly because the sea ice thickness in the Norwegian Arctic regions are not that different across climate warming scenarios.
10 minutes.
Thank you. At the AU level, there are 4 Arctic AUs in USA show positive Arctic offshore oil productions under RCP 8.5, although production at the whole basin is relatively small, which you can barely see from this figure. And majority of the production comes from the Alaskan platform, where the sea ice condition is more favorable for offshore oil production. And then the offshore oil potential at Alaskan platform is also higher than other AUs. In the case of Russia, here there are more AUs in general and more AUs with positive production than USA, as you can tell. And also there are 2 Arctic AUs showing positive Arctic offshore production in the reference. So 4 in the 2.6 and even more in the 8.5. And one thing I noticed is that in the North Barents Sea, which is shown in the bright blue color, production could start 20 years earlier in the RCP 8.5 than the RCP 2.6. So with a very quick show of the key preliminary results, hopefully you can get a sense of the overall methodology and what we can do with this newly developed model representation of Arctic offshore oil in JCGCRI. In summary, we explore the future of the future of offshore oil extraction in the Arctic as the climate change has led to sea ice loss and will continue to open up new regions in the Arctic for human activities. And we implement this undiscovered oil potential at the assessment unit level with the AU-specific Arctic offshore oil resource reserve technologies. We also incorporate the uncertainty of sea ice projections from CMIP6 and then the seasonality of sea ice thickness for consideration of offshore oil extraction technology implementation and the associated cost estimates. We see that Russia starts to tap Arctic offshore oil in the beginning of our modeling periods, likely in the south of Barents Sea, while USA and Canada will now not likely tap the oil until the last few decades of the century. So comparing across climate scenarios, RCP 8.5 in general leads to higher and earlier Arctic offshore oil production. Lastly, I didn't show associated results here, but we found that the production of Arctic offshore oil is not likely to alter the global pattern of total crude oil production and trade. So I want to acknowledge the funding source at stake here. With that, I'm happy to take questions, and you're also welcome to contact me through the email. Thank you.
Thank you, Ying. Let's go ahead and take any question or two for Ying, and then we can open to broader discussion as well. So we have Wei, had your hand up.
Yeah, thank you, Ying. That was really interesting. I want to ask a question about the demand side responses, because my guess is that in the 8.5, the demand is also going to be higher because we're going to depend more on oil. So to what extent is your result driven by demand, and to what extent is driven by this supply story?
Yeah, that's a really good point. I guess I didn't make it clear what my scenarios are. So the reference here is actually the GChem SSP5. So we use that as the reference. And then reference 2.6 is the GChem SSP5 with the sea ice projections under RCP 2.6. So I haven't really tried a different GChem SSP under the same set of sea ice projections, so I cannot really answer the second question you have there. But I do feel a lot of the range of the results are from the different sea ice projections from the climate warming scenarios.
Can I ask a follow-up question if there's no other questions?
Yeah, go ahead.
Yeah, could you also talk a little bit more about how trade is being modeled here? Do you imagine in the future, there's still just a global market for oil, or there's some fragmentation because of geopolitics and other reasons? Because I guess that would also matter the results you're showing here.
Yeah, so that's a good question. So the Arctic offshore oil, for example, is a sub-resource under the crude oil. So it will be traded as the same product as the oil before it enters the international market for trade. So basically, the Arctic oil, the unconventional oil, and also the regular crude oil would all together goes to the regional oil before it goes to the international traded market. So that's how it's currently represented in GChem. And also we have the basically the oil demand represented in GChem as well, where in the later half of the century, the oil demand would go down. And then I guess the demand driven factor for the Arctic production of offshore oil would also go down in the later half. So that would also affect the international trading and demand for the Arctic oil. But I guess another factor for why Arctic oil is not that a big factor in the regional market and international market is that the extraction cost for Arctic oil is comparatively higher than regular oil. So not all the potential in the Arctic would be extracted, at least under the scenarios we tested. In another ongoing scenario rounds, we are trying to put the subsidy for Arctic offshore oil. So for example, some countries like Russia may have the ambition to explore the Arctic for oil and gas development. So if we put subsidy, maybe it can tell us a different story and of course a different pattern for the international trade of the Arctic oil as well. I don't know if that answers your question.
Great. Brian.
Yeah, thanks. I wanted to ask a broader question that I guess goes to really any of the talks that we've had in both sessions. And this is kind of driven by what I was talking about yesterday, and that's the reason it's kind of stuck in my head is using integrated assessment models to model impacts where the question is how severe could these get? And so not all, but most of the talks that we saw use the IAMs to eventually produce an estimate of the impact on GDP. And so, two questions about that. One is, there's this ongoing debate about why a lot of statistical approaches to estimating GDP impacts tend to get larger estimates than IAMs, and whether people have thought about that question in this context. In that debate, it comes down a lot to whether the impacts affect the growth rate or the level of GDP, and maybe thinking about that in the context of how are these things being implemented in IAMs. And the other, and I think this came up in the chat a little bit, is metrics for impacts beyond GDP. And in some cases, those are being assumed as inputs, like saying, okay, we're going to have this particular health impact. Let's use the IAM to see how it affects GDP. So that's fine. But in other cases, it seems like some of those other impacts in non-monetary terms or non-GDP terms, even if they're monetary, are an endogenous result from the analysis, and that maybe emphasizing those more along with GDP might be a useful approach. And I'm wondering what people think the scope for doing that sort of shift the focus a little bit away from ultimately always looking for what's the GDP impact.
I would say that things are moving in that direction. I would say in my experience, particularly in the area of health and health impacts, I've been seeing increasing amount of work that's focusing on trying to capture more than just GDP impacts related in the area of health. But I think it's a great point to raise, and I think the community needs to increasingly be moving in this direction. There's this whole concept of kind of inclusive wealth that's trying to move beyond just GDP to capture, other things that are important to societies. But I think I agree with you that there's a lot more that can and should be done. And I, to be honest, haven't given it too much thought myself, be outside of the area of health, where I think there's some more like obvious areas that you could push beyond GDP. But I'd love to hear others' ideas of things that we could be capturing in other sectors that are beyond GDP.
Yeah, if I can say something, I think this is a very interesting, very interesting discussion. And I was also looking forward to hearing your thoughts on this, Jennifer, about the impacts of water on biodiversity, which is also like a non-GDP related issue. And we typically look at biodiversity loss as losses of ecosystem services, so for people, but well, at least in my experience, we haven't really looked at the impact of water impacts on biodiversity and how that could be included as well. So that might be very interesting to include that as well.
Yeah, I agree. And I think we have, while it's still an area that hasn't had as much attention, it tends to be put in also kind of the framing of how do we get it into a GDP, right? Because it's like, can we quantify it in terms of ecosystem services or, natural capital? And it's our way of kind of taking things that we know matter and putting it into these frameworks of analyses that we're used to using and quantifying in terms of GDP. And I think that there's definitely value in that work and areas to push that further. And I think a lot more could be done in terms of biodiversity, and just touching that on the fringes so far. But I think the kind of even pushing it even a step further, where we haven't really made much ground in the community, is beyond GDP. Like, how can we get beyond taking these, health impacts or biodiversity impacts and giving some type of metric that's not just GDP centric? And I don't know the answer to that. Like I said, I think there's value in trying to put it in the kind of GDP economic framework. But what could we do even beyond that, I think, is also a nice question.
Yeah, and maybe to add on that, because we're also trying to develop new damage functions which have as output or on the y-axis just GDP losses, and I think that's also very limiting yourself or ourselves in that sense. And I would love to have this split or this coherent set of on the one hand this true biophysical impacts that people understand, like what the amount of people at risk, the amount of species lost, and these kind of things, but then also the connection with GDP, because I think that's still important for policymakers. They keep asking, like, what's the benefit cost ratio? If you want to calculate social cost of carbon, you need this GDP, but you also really need for transparency and for public acceptance, that's also this more tangible metrics. If I tell my parents about GDP, they have no idea. But if I tell them about species loss, then it's much more interesting. So yeah, I think that as a community, we also need to move towards that. So yeah, thanks for your support on that as well.
I was wondering if others are looking at along those same lines, how different groups within a country or region are impacted. So rather than just kind of the average GDP per capita? Do we, have other people started looking at, rural versus urban or different income groups or within countries? Wei has.
Yeah, I think also super important in the US, this is the new push, right? It's the equity issue, the environmental justice issue has really risen to the surface. And I think we'll be seeing, and it's great, I think we'll be seeing more of that coming out. And we have the beginnings of tools to look at different income groups. And I know, Stephanie, in your group, you're working on that too. And I think that's really important and gives us further insight into not just overall GDP or economic impacts, but how specific vulnerable population groups could be affected. So that's great to raise that also.
Wei?
Yeah, I give a thumb up for it because I think that's super important. We got a new NSF grant, and we're currently looking at the distribution of health co-benefits from mitigation, both globally and also within the United States. And I think the really important point there is that, first of all, this echoes back to, Brian, what you were saying yesterday, that as we respond to climate change, there will be emerging new risks from mitigation. And on top of that, people are going to experience different kind of co-benefits. For example, if we use electric vehicles more, then it's going to be urban people who benefit more. Whereas if we change the way we use bioenergy in the residential sector, then it's going to be a different group of people who are going to benefit from it. And this is still from the benefit perspective. We have even been looking at some of the health co-harms that could occur if we have a large-scale bioenergy use that really change the way we use land use, and as a result, it leads to deforestation, leads to more bioenergy use in the residential sector. So this is just to say, I personally, I really think this is an important discussion, and I would love to continue discussing this with the community here.
So thank you, everyone.